Greetings, and welcome to Secrets of History at Night, where our sense of wonder finds a cozy spot and scientific exploration takes its time to unwind. Tonight, we embark on a journey into a question as old as our planet's deepest oceans and as expansive as the heavens above. It's a query you might not have ever considered, one that lies in plain view, washing onto our shores and swirling in our morning brews. Where did all the water on Earth originate? It's rather remarkable, isn't it? Our planet, this precious pale blue sphere, is awash in water. Vast oceans embracing continents, clouds drifting gracefully across the sky, and rivers that etch the land like silver ribbons. It's so commonplace that we often forget its truly extraordinary nature. The seas seem eternal, but they certainly had a genesis, and that beginning might be far older, much colder, and considerably stranger than you might imagine. Before we venture into the cosmic clouds and ancient terrestrial remnants, allow me to ask, what time is it where you are? Is it your morning coffee, a tranquil afternoon, or the hushed moments of a midnight rain? If you find this exploration to be a calming experience, if it sparks a sense of wonder as you gaze out your window, I would be most appreciative if you were to like this video, subscribe to our channel, or perhaps share it with someone else navigating the currents of time and curiosity. So, please settle in, calm your thoughts, and let us commence our exploration. For in the grand narrative of Earth, water serves as both the ink and the very paper upon which its story is written. And to discover its origin, we must journey beyond the atmosphere, transcending time itself to a moment predating any memory of the sea. Approximately 4.6 billion years ago, Earth was not born as a serene blue sphere, but rather as a fiery inferno, parched, molten, and unforgiving. Yet today, over 70% of its surface is covered by liquid water, a delicate, rare, and life-sustaining phenomenon. But how did it arrive here? Was it an intrinsic component of Earth's formation, hidden within its molten core? Or did it journey from elsewhere, perhaps delivered by icy celestial bodies from the vastness of space? Tonight, we shall follow the water's narrative, from interstellar ice and the deep secrets of the mantle to violent collisions and gentle downpours. To comprehend the origin of Earth's water, we must rewind far, far back. Back before the oceans existed, before the rivers flowed, before Earth even possessed a discernible surface. We must journey to the very inception. Within the quiet confines beneath Honolulu, housed in a structure that could easily be mistaken for a mere university annex, a minuscule fragment of Earth's ancient memory once ignited a chain of inquiries that reached all the way to the distant stars. The year was 2014, and a team of geochemists led by Dr. Lydia Hallis was meticulously examining microscopic inclusions found within a basalt rock of immense age. This artifact, a remnant from Earth's early mantle, had been brought to the surface by volcanic activity. These inclusions, mere specks of glass entombed within the mineral olivine, carried within them the distinct isotopic signatures, clues, almost whispers, from a time when Earth was still in its nascent stages of formation. And within these clues they discovered something peculiar: deuterium, a heavier form of hydrogen. The ratio of deuterium to hydrogen, often abbreviated as DH, acts as a kind of cosmic fingerprint. Different sources of water throughout the universe exhibit distinct ratios. What Dr. Hallis's team unearthed was this: the DH ratio found in those mantle samples was considerably lower than that observed in Earth's present-day oceans. It was significantly lower than the signature typically carried by comets. In fact, it bore a striking resemblance to the DH ratios detected in specific types of meteorites, particularly carbonaceous chondrites, those primitive ancient rocks from space. This subtle chemical discrepancy unfurled a window into the past, allowing the starlight of discovery to stream through. For in that pivotal moment, they grasped something extraordinary. Earth's water may not have originated from comets, as had been widely presumed for so long. It might have originated from something even more ancient, from the very fundamental building blocks that constituted the planet itself. However, to fully comprehend this, we must first grasp the process of Earth's formation, which was not a gentle miracle but a tumultuous storm of celestial debris. The solar system burst into existence amidst profound chaos. A vast rotating disk of gas and dust swirled around the nascent sun, a turbulent, incandescent, and intensely hot environment. Within this swirling disk, minuscule grains of dust began to adhere to one another, then coalesce into larger clumps, and subsequently collide. Over the course of millions of years, these aggregations grew into progressively larger celestial bodies, planetesimals, and then protoplanets. It was a cosmic demolition derby, where gravity served as both the relentless hammer and the binding adhesive. Our Earth commenced its existence as one of these protoplanets, a growing sphere of rock and metal, assembled through the violent amalgamation of countless smaller fragments. And some of these constituent pieces carried water, though not in the form we recognize today, not as oceans or rain. This was water intrinsically trapped within minerals, tightly bound within the crystalline structures of silicates, hidden within the dust. These hydrated minerals had formed in the frigid outer regions of the solar nebula, far removed from the sun's pervasive warmth. They embarked on a journey inward, transported by migrating asteroids and subtle gravitational influences. Upon colliding with Earth, they released their ancient moisture not in gentle droplets, but in explosive bursts of steam. And herein lies the paradox. Earth began its existence intensely hot, extremely hot, hot enough to vaporize anything containing moisture. Its surface was molten, and its atmosphere, if it could be so called, was more of a transient veil of vaporized rock. So, how did any water manage to survive this inferno? Some of it, undoubtedly, did not. A substantial portion of the water delivered in the earliest stages was likely lost, either vaporized into the void by the solar wind or forcefully ejected by the immense energy of impacts. However, not all of it was obliterated. Deep beneath the surface, some water found sanctuary, locked away within mineral structures, gradually sinking into Earth's developing mantle. And as the magma oceans began to cool and the crust started to form, the process of volcanic outgassing commenced. Steam, hydrogen, oxygen, carbon dioxide, and among these gases, water vapor. The first rains descended, not a gentle drizzle but torrential downpours that persisted for millennia. Rain that transformed fire into oceans. Yet, here is the compelling twist. If Earth's water originated from these ancient water-bearing planetesimals, from these chondrites, then Earth was inherently destined to be a water-rich planet from its very inception. It may not have appeared blue initially, but it was certainly damp at its core. This hypothesis introduces a fascinating possibility. The essential components for oceans were intrinsically woven into the planet's fundamental recipe from the very beginning. Nevertheless, the complete picture remains elusive, as there is another crucial piece to this intricate puzzle. Consider those dazzling comets that streak across our night sky, appearing like fleeting whispers from the outer darkness. For decades, comets were considered the primary suspects in the enigmatic origin of Earth's water. After all, they are predominantly composed of ice. What could be more logical? These icy visitors from the Kuiper Belt or the distant Oort cloud, impacting the nascent Earth and melting into our vast seas. Indeed, during Earth's early history, impacts were a frequent, violent, and planet-shaping occurrence. The late heavy bombardment, occurring around 4 billion years ago, was a period characterized by relentless cosmic bombardment, not of water, but of rock and ice. If comets were indeed responsible for Earth's water, that era would have been their prime opportunity. However, as we have observed when meticulously measuring their isotopic signatures, their DH ratios, something did not align. Most comets exhibit excessively high deuterium levels. Their water composition is chemically dissimilar to that of Earth. It is close, but not an exact match. It's akin to discovering a puzzle piece that almost fits, but ultimately refuses to interlock. Certain comets, particularly those originating from the asteroid belt rather than the far-flung outer solar system, do possess DH ratios that are closer to Earth's. But even in these cases, the alignment is not perfect. Furthermore, the sheer volume of water they could have delivered is insufficient to account for our planet's oceans. It is plausible that comets played a minor role, perhaps contributing a light drizzle rather than a significant flood. It is the carbonaceous chondrites, those ancient meteorites, that now appear to hold the most convincing evidence. They formed in the early stages of the solar system, embarked on extensive journeys, and experienced numerous collisions. In doing so, they became the unwitting couriers of Earth's oceans. Yet, this narrative, rich with isotopic analysis and orbital mechanics, still leaves ample room for profound wonder. Because even if the water originated from space rocks, the very moment it descended upon this world, it fundamentally transformed everything. Envision it: a scorching hot Earth, its crust fissured with molten magma, its sky thick with vapor. Then the advent of the first true storm, not one driven by lightning, but by rain, cascading sheets of it, falling for centuries, sculpting the initial riverbeds, filling the nascent basins, and ultimately giving birth to the very first sea. Water, born from stone and fire, draped the planet in the promise of future life. So, the next time you immerse your fingers in the ocean, remember that you are touching a molecule that once traversed the vastness of space, intimately bound to a fragment of rock older than Earth itself. It journeyed across billions of miles. It endured impacts, immense heat, and crushing pressures, yet it persisted, ready to become an integral part of an ocean, a cloud, a tear, a breath. Water did not merely arrive on Earth, it chose to remain. Before the seas churned, before clouds even had the capacity to form, Earth existed as a smoldering, rotating enigma, suspended within the nascent solar system. Picture it not as the verdant blue marble we recognize today, but as a tempestuous sphere of rock and intense heat, a molten orb glowing with a faint reddish hue, reminiscent of the solitary eye of a forgotten forge. Its surface was not yet solid, it was a restless ocean of lava, perpetually agitated by impacts and constantly reshaped by the sheer chaos of its own infancy. This was Earth's state during its initial few million years. In this early iteration of the planet, water, if it existed at all, was not something one could consume or swim in. It was ephemeral, a vapor, a chemical whisper subtly bound within rocks or drifting like steam through an atmosphere heavily laden with sulfur, carbon dioxide, and silicates. In that era, the atmosphere bore no resemblance to the gentle, breathable blue envelope we inhale today. It was suffocating and dense, more akin to a plume of smoke than a sky. Volcanic outgassing relentlessly injected greenhouse gases into this atmosphere, while the sun, considerably dimmer than it is now, cast a pale light upon a world that had yet to form any oceans to capture it. Continents were absent, as were stable crustal formations. Any landmass that did emerge was temporary, solidifying briefly as it cooled, but frequently fractured anew by fresh flows of magma. And within this ever-shifting seascape of fire, deep below the developing crust, minerals began to sequester hydrogen and oxygen, the fundamental constituents of water. These elements were held captive within silicate structures, destined to be liberated eventually by intense heat and pressure. This primordial world was governed by forces we can barely conceive of today. Cataclysmic impacts were commonplace. Some were so colossal they had the power to melt entire hemispheres. One such event, arguably the most significant, is theorized to have been responsible for the formation of the Moon itself. A Mars-sized body, known as Theia, collided with the proto-Earth, ejecting a sufficient quantity of debris to coalesce into a satellite and forever altering the trajectory of our young planet. Yet, these cataclysms were not endpoints. They were, in fact, the very beginnings. Each impact, each fissure that opened in the crust, provided new conduits for the escape of internal gases: hydrogen, carbon monoxide, and water vapor. As the planet gradually cooled, these gases began to condense. What had once ascended skyward as vapors started to descend. The first rains, undeniably acidic and alien in nature, commenced their descent. Imagine the sound they made, not a gentle patter, but a continuous hiss. Raindrops striking molten rock, instantly vaporizing. Rivers could not yet form. The land was not stable enough to carve them. Instead, pools of water evaporated as rapidly as they formed. However, slowly and relentlessly, the surface began to undergo transformation. The cooling process spanned a considerable duration, hundreds of millions of years. But eventually, the magma oceans receded, yielding to a solid crust, albeit one that was thin and precarious. It fractured and buckled under its own internal heat, releasing further gases, more steam, and consequently offering increased opportunities for water to persist. This epoch is known as the Hadean Eon, a name derived from Hades, the underworld, a fitting appellation for a realm of such intense fury and fire. Yet, even within this inferno, the fundamental prerequisites for life were quietly being assembled. And here, we must pause our narrative. For to discuss the presence of water on Earth without delving into the planet's internal structure would be to omit the very heart of the story. Miles beneath your feet, far below the crust, lies a region designated as the mantle. While solid, it possesses a temperature high enough to enable it to flow over geological timescales. It is within this mantle that Earth safeguards its most ancient secrets. And remarkably, we now understand that the mantle harbors an amount of water equivalent to, or perhaps even exceeding, all the oceans combined. This water is not contained within lakes or subterranean rivers, but rather locked within minerals such as ringwoodite and wadsleyite, crystalline structures capable of trapping water molecules within their lattice, holding them under pressures far beyond anything encountered at the surface. This deeply embedded water is not readily accessible. It does not slosh or drip, but its existence is undeniably real. And it reveals something truly astonishing. Earth did not simply acquire its water from external sources. It may have matured, becoming hydrated from its core outwards. For those planetesimals, the chondrites and early celestial rocks, not only delivered water to the surface but also to the planet's core, to the very foundations of its structure. And some of that primordial water never departed. The implications of this are nothing short of staggering. It signifies that water was not a late arrival. It was a foundational element. It was present during the critical phase of differentiation, when Earth's distinct layers were forming. It was present during the cataclysmic impact that formed the Moon. It was likely present when the first seas finally collected in basins cool enough to retain them. Let us turn our attention to those nascent seas. Once the planet's surface had cooled sufficiently to solidify and the atmosphere had accumulated a substantial amount of vapor, Earth's very first true oceans began to emerge. This was not an instantaneous event. There was no singular moment when an observer could gaze upon a gleaming blue expanse. Rather, over an extended period, puddles coalesced into lakes. Lakes merged to form seas, and eventually the vast oceans took shape. These early oceans were shallower by today's standards, and their forms were continuously altered by volcanic activity, meteor impacts, and the relentless shifts of tectonic plates. The skies above them were not yet the familiar blue. Devoid of free oxygen, the atmosphere was a hazy mixture of methane, ammonia, and carbon dioxide. The sun's ultraviolet rays penetrated this atmosphere with ease, and in the absence of an ozone layer, radiation relentlessly bombarded the surface. Yet, despite all these formidable conditions, the oceans persevered, held in place not solely by gravity, but by Earth's unique equilibrium of heat, pressure, and atmospheric conditions. It was a delicate balance, a slight shift closer to the sun, and water might never have condensed. A slight shift farther away, and it might have remained frozen indefinitely. But here, within this precious zone, known as the habitable zone, it persisted. Still, these early oceans bore no resemblance to the ones we know today. They were acidic, possibly greenish in hue due to dissolved iron, and warm, constantly churned by geothermal activity emanating from below. Hydrothermal vents, essentially underwater geysers powered by volcanic heat, spewed minerals and warmth into the depths, creating environments that many scientists now believe may have served as the very cradle of life. There were no coral reefs, no fish, only water, rock, heat, and an immense span of time. And perhaps something more. Organic molecules drifting in from space, or spontaneously forming within the primordial soup of early Earth. Amino acids, simple sugars, the fundamental building blocks of biology. Within these ancient waters, chemistry found the space to expand, to experiment, to combine and recombine, and perhaps, quietly and gradually, to awaken. Because before Earth became a home, before it was lush, green, and teeming with sound, it was simply wet. A planet characterized by storms, seas, and profound silence. And within that silence, something began to stir. To truly grasp the ultimate origin of Earth's water, not merely how it arrived, but how it took root, persisted, and fundamentally reshaped the planet's very nature, we must follow a trace etched not in the oceans, but in isotopes. This journey commences with hydrogen, the most abundant element in the universe. Light, ancient, forged in the very initial moments following the Big Bang. However, hydrogen is not a monolithic element. Some of its atoms possess an additional neutron, a variant known as deuterium. While still hydrogen, it is notably heavier. The ratio between regular hydrogen and deuterium functions akin to a cosmic passport stamp, indicating the extraterrestrial journey of a specific water sample, whether it coalesced in the distant reaches of the solar system, formed on a frigid asteroid, or emerged from volcanic gases. This is the deuterium to hydrogen ratio, or DH ratio. Earth's seawater exhibits a distinct DH ratio. For decades, scientists have meticulously compared this ratio with known sources: icy comets, asteroids, meteorites, and even the solar wind. The findings were more than mere data points, they were definitive fingerprints, and they pointed towards something quite peculiar. Let us first consider comets. Those icy wanderers from the solar system's outermost fringes appear to be the ideal conduits for delivering water. However, the majority of comets that have been studied, such as Halley's Comet or Comet Hale-Bopp, possess DH ratios that are significantly higher than that of Earth. If Earth's oceans were indeed sourced from these itinerant icy bodies, their chemical composition would necessarily be different. Yet, they are not. Certain comets originating from the Kuiper Belt do exhibit ratios that more closely align with Earth's, but these instances are the exception, not the prevailing rule. Furthermore, even if every single one of them had impacted Earth, they would not have delivered a sufficient volume of water to fill our oceans. The notion of oceans as gifts from comets is appealing, but the empirical data from both mathematics and chemistry suggest otherwise. This brings us to meteorites, specifically a less common classification known as carbonaceous chondrites. These are among the most ancient solid objects within the solar system. They are essentially tiny time capsules that formed in the dusty midplane of the solar nebula over 4.5 billion years ago. Some of these meteorites never underwent the melting and differentiation processes that reshaped larger celestial bodies. Consequently, they preserve their pristine, ancient chemistry, including the presence of water. As researchers began to analyze their DH ratios, a discernible pattern emerged. These ratios closely matched those found in Earth's oceans, not merely with a degree of similarity, but with remarkable precision. These meteorites contain hydrated minerals, providing tangible evidence that water was not simply transported by them, but was intrinsically incorporated into their very structure. Furthermore, their isotopic fingerprints strongly suggest that they originated in a region of the solar system situated not far from where Earth itself was assembled, specifically within the inner asteroid belt. Suddenly, a coherent picture began to materialize. Earth did not wait for comets to deliver its water. It inherited it, not in the form of ice, but as hydrated rock. The delivery mechanism was not in vast quantities, but rather through billions of minuscule grains. This process likely commenced during the planet's accretionary phase. As Earth grew, it continuously absorbed rocky material, some of which was dry, while other portions were hydrated. The hydrated components contained silicates rich in oxygen-hydrogen bonds, effectively meaning water was chemically bound within minerals. This was not surface water. It was deeply sequestered, trapped within the developing mantle, and when the planet underwent differentiation, a process where denser elements like iron sank towards the center to form the core and lighter silicates ascended to constitute the mantle, those hydrated minerals were carried along with this internal movement. But herein lies the crucial element. This was not merely a passive form of storage, it was a process of transformation. Over geological time, as internal heat accumulated and volcanic activity intensified, this bound water was gradually released. The Earth began to release gases through outgassing, not merely nitrogen or other inert elements, but water vapor. Plumes of steam would rise from fissures and emerge from the mid-ocean ridges. The planet exhaled, and its atmosphere, thick and volatile, became saturated. Eventually, as the planet's surface cooled sufficiently, the water began to condense. The rains commenced, and they did not cease. This was not a singular storm event, but rather an epic of continuous deluge, a hydrological era where clouds formed incessantly and rain pounded the surface like a monumental baptism. Pools of water converged to form seas, and basins filled. Water collected in the low-lying areas, carving pathways, shaping valleys, even as the planet's crust itself continued to shift and buckle beneath. However, there exists an alternative theory, one that posits an even more ancient, colder, and stranger origin for Earth's water. Some scientists propose that Earth's water began to arrive even before the planet itself was fully formed, originating from the very dust particles from which it coalesced. In the frigid expanse of the solar nebula, far beyond the warmth of the young sun, ices formed not only of water, but also of carbon monoxide, methane, and ammonia. These ices coated the silicate dust grains, the raw material destined to form planets. As turbulence and gravitational forces stirred the protoplanetary disk, some of these icy grains drifted inward. They did not immediately melt. Instead, they adhered to growing clumps of matter. They contributed their mass to planetesimals, and in doing so, they brought their embedded water with them. In this particular model, Earth's hydration is not in subsequent addition. It is primordial. The planet did not become hydrated. It was born hydrated, at least in certain components. This perspective might offer an explanation for a curious phenomenon: the remarkable consistency of water's isotopic signature across the entire planet. From the deep mantle rocks to the surface oceans, from polar ice caps to subterranean aquifers, the DH ratio remains remarkably uniform. Such a level of uniformity strongly suggests a shared origin, rather than a piecemeal collection from disparate deliveries, pointing instead to a foundational source. However, the question of retention still remains pertinent. Even if water arrived early in Earth's history, how did it manage to stay? The early Earth was intensely hot, sufficiently so to vaporize water instantly and to strip lighter gases from the atmosphere. Some researchers posit that Earth's initial oceans may have formed and subsequently vanished, lost to space due to the solar wind or through immense impacts. So, why did not all of the water escape? There are two primary reasons. Firstly, Earth possesses significant mass. Its gravitational pull is sufficiently strong to retain heavier molecules, such as water vapor, even during periods of intense celestial activity. By the time water became plentiful on the surface, Earth had started to develop a magnetosphere, a protective magnetic field generated by the rotation of its molten iron core. This shield deflected the solar wind, safeguarding the atmosphere and the water within it. Without this magnetosphere, Earth could have faced the same fate as Mars, a planet that once possessed water but lost most of it to space. Therefore, the true marvel is not solely Earth's acquisition of water, but its ability to retain it. It rained for an extended period, cooled sufficiently rapidly, and protected itself so effectively that it could nurture the oceans we recognize today. Water arrived early, it arrived frequently, but most importantly it remained, and in its persistence, everything transformed. Let us revisit Earth, not as a molten sphere or freshly crusted orb, but as a world poised at a precipice, beginning to wear its oceans like a loosely fitting garment. Something profound was shifting, not in an instant, but over millions of years, as water transitioned from a vaporized dream to a planetary feature. The alteration was not subtle. It encompassed the planet's entire geochemistry. The cycles of heat and pressure dictated whether water would remain locked within minerals or erupt as steam. This is where Earth's deep mantle re-enters the narrative, not as a peripheral detail, but as a central protagonist. The water cycle we are familiar with, the perpetual ascent and descent of evaporation, condensation, and precipitation, is not merely a surface phenomenon. There exists another cycle beneath our feet, one that might be as ancient and vital, the deep water cycle. It functions as follows. As tectonic plates shift, grinding, sinking, and colliding, some are driven downwards into the mantle through a process known as subduction. Along with them, they pull seawater, not in liquid form, but bound within hydrated minerals like serpentine. This water descends deep, sometimes hundreds of kilometers, where immense pressures and temperatures compress and transform it into new states. While some remains trapped, a significant portion eventually returns, released from the rock by heat, ascending through magma and erupting from volcanoes or mid-ocean ridges as steam. Over time, this cycle establishes a planetary rhythm, water entering, water exiting. Not rapidly, not dramatically, but consistently and essentially. It is this internal respiration of the earth that may have enabled the oceans to achieve a stable volume. Without it, water might have continuously accumulated or vanished entirely. However, with it, the oceans became sustainable, a layer rather than a flood. Nevertheless, another catalyst played a role in transforming oceans from chemical reservoirs into biological incubators: oxygen. Not the oxygen we inhale today, not yet, but its gradual, subtle introduction was intrinsically linked to life itself. Approximately 3.8 billion years ago, as the nascent ocean stabilized, something extraordinary commenced. The earliest indications of life, in the form of simple, ancient, and astonishing microbes. These organisms did not require oxygen for survival. In fact, they would have found it detrimental. Instead, they thrived on chemistry, harnessing energy from hydrothermal vents or sunlight filtered through a hazy sky to power their rudimentary metabolisms. Among these primeval life forms were cyanobacteria, minute architects of planetary change. Inhabiting shallow waters, they formed clusters within mats or mounds known as stromatolites. And they accomplished something unprecedented. They performed photosynthesis. Utilizing sunlight, they converted carbon dioxide and water into energy, releasing oxygen as a byproduct. Initially, this released oxygen did not persist. It bonded with iron present in the oceans, creating rust-colored rock formations that we still discover today. Banded iron formations, geological evidence of Earth's gradual oxidation. Eventually, however, the oxygen began to accumulate, first in the oceans and then in the atmosphere. This marked the commencement of what scientists refer to as the Great Oxidation Event, around 2.4 billion years ago. It was not a swift process, nor was it uniform, but it fundamentally reshaped the planet's chemistry, including its water. Oceans became less acidic, new minerals emerged, and biological complexity increased. Life adapted, some perished, while others evolved, and the atmosphere began its slow transformation toward the breathable mixture we recognize today. All of this was contingent upon water. Water transported carbon, water housed the microbes, water stabilized the climate, moderated temperatures, and facilitated reactions that would be impossible in an arid world. Yet, water was not merely a passive medium. It sculpted the very surface of the earth. Over time, it carved valleys, eroded mountains, and generated the sediments that would form soil. It created rivers that reshaped continents and glaciers that ground rock into dust, thereby altering entire landscapes. More significantly, however, water regulated the planet's thermostat. Thanks to its substantial heat capacity, water can absorb considerable amounts of heat without experiencing a significant temperature rise. This characteristic helped Earth avoid the extreme climatic fluctuations that afflict other planets, allowing for moderation, consistency, and habitability. Furthermore, water enabled the establishment of the carbonate-silicate cycle, a long-term feedback mechanism wherein atmospheric carbon dioxide is extracted through weathering, stored in rocks, and ultimately reintroduced via volcanic activity. Without this equilibrium, Earth might have succumbed to a runaway greenhouse effect like Venus, or become a frozen wasteland like Mars. Instead, it remained temperate, stable, and wet. There is also the matter of Earth's distinctive hydrosphere when compared to its rocky neighbors. Venus and Mars may have once harbored water, possibly even oceans, but neither managed to retain it. Venus, being closer to the Sun, experienced a runaway greenhouse effect, causing its water to vaporize and dissociate under solar radiation. The hydrogen escaped, the oxygen bonded with the rocks, leaving the planet parched beneath a crushing atmosphere of carbon dioxide. Mars, being smaller and more distant, lost its internal heat more rapidly. Its magnetic field weakened, and without protection, solar winds stripped away its atmosphere. Any remaining water either froze or seeped underground, causing its rivers to dry up and its seas to vanish. Only Earth managed to retain its water due to its mass, its magnetic field, its distance from the Sun, its internal cycles, and indeed, its good fortune. It was, in many respects, a perfect convergence of factors, with water being both the cause and the consequence. From stardust to storm clouds, from minerals to monsoons, water's journey was not merely a delivery, but a profound transformation, a shaping force, a foundational element, and its influence continues to this day. Every drop in your glass contains atoms that predate Earth itself. Hydrogen forged in the Big Bang and oxygen born in dying stars. These elements coalesced repeatedly in space, in stone, and in seas. And here they are, on your tongue, in your blood, in the tears we shed, and in the rain that nourishes the forests. The water, we know, is ancient, restless, and utterly irreplaceable. As we trace its origins, we witness not only how water arrived on Earth, but how, through water, Earth became itself. When Earth's surface finally cooled sufficiently to contain oceans, the presence of water did more than simply signify a new phase in the planet's evolution. It fundamentally altered the possibilities for planetary development. This was not merely the appearance of a new chemical compound, but the initiation of a cascade effect. Water, seemingly simple, became a catalyst for change so widespread that it affected every aspect of Earth, from the crust beneath to the skies above. It did not just fill basins, it began to shape continents, regulate climate, and alter the planet's chemistry in irreversible ways. To begin, we must return our attention to the crust, Earth's fractured outer shell floating upon the hot, pliable mantle below. With the arrival of water, this crust underwent a subtle yet profound weakening. The significance of this lies in the fact that water acts as a lubricant within geological systems. It lowers the melting point of rocks, infiltrates fault lines, and seeps between mineral grains, increasing their mobility. When subducted into the mantle, it causes rocks to melt more readily, thereby fueling volcanism. In essence, water made plate tectonics possible, not merely in its current form, but the very capacity for Earth's surface to shift, recycle, and regenerate. Without water, Earth's lithosphere might have remained rigid and static, akin to the surfaces of Mercury or the Moon. Instead, it fractured into mobile plates. These plates commenced their movement, converging, diverging, and sliding past one another, giving rise to mountain ranges, oceanic trenches, and island arcs. This motion imbued Earth with its dynamic geology, a process that continues to this day. Earthquakes, volcanoes, and rift valleys all bear the subtle influence of water deep within the planet. However, the consequences extended beyond the crust. As the oceans deepened, they transformed into vast chemical laboratories. Rainwater, slightly acidic due to dissolved gases, began to erode the early land masses. This process, known as weathering, broke down rocks into sediments and released minerals into the sea. The runoff supplied the oceans with calcium, magnesium, sodium, and potassium, the elemental components that continue to define seawater today. Over millions of years, these reactions extracted carbon dioxide from the atmosphere, sequestering it in carbonate rocks and consequently cooling the planet. This marked the inception of Earth's long-term carbon cycle, a planetary thermostat. Water was not merely sculpting the surface, it was dictating the climate. Simultaneously, the seas became rich in dissolved iron, a consequence of the absence of free oxygen. This set the stage for one of Earth's most remarkable transformations, the oxygenation of the atmosphere. We have previously touched upon this, specifically the role of cyanobacteria and their photosynthetic processes. However, this is where the chain reaction truly commences. Cyanobacteria, inhabiting the shallow fringes of ancient oceans, began to produce oxygen. Initially, this oxygen did not accumulate in the air. It reacted with iron dissolved in the water, forming iron oxide, rust, which precipitated and settled on the seafloor. These deposits would eventually become the banded iron formations that modern geologists excavate and study. Only after the available iron was saturated did oxygen begin to gather in the oceans, and subsequently in the atmosphere. This gradual rise of oxygen, the Great Oxidation Event, profoundly altered the biosphere. Oxygen is reactive. It breaks chemical bonds and fuels both combustion and metabolism. When it first appeared in significant quantities, it proved toxic to the majority of existing life forms. Entire microbial communities were annihilated. Extinction by oxidation. However, for other organisms, those capable of adapting or evolving, oxygen offered something new: energy in vast amounts. Aerobic respiration, which utilizes oxygen to extract energy from sustenance, is considerably more efficient than anaerobic methods. This advancement allowed life to become more complex, more active, and more ambitious. This, too, was a water-driven change. Without oceans, there would have been no environment for cyanobacteria to flourish. Without water, there would have been no medium for oxygen to dissolve, disperse, and react. Thus, water created the stage, and life responded to its cue. Meanwhile, on the surface, water continued its quiet work, fracturing rocks, smoothing landscapes, and transporting sediments. Glaciers formed in higher latitudes and altitudes, carving valleys and grinding mountains into fine silt. Rivers meandered across the land like silver arteries, creating deltas and fertile floodplains. The hydrological cycle, the ceaseless loop of evaporation, condensation, and precipitation, evolved into one of Earth's dominant forces. Powered by solar energy, it redistributed heat, shaped climate zones, and delivered fresh water to the continents. Accompanying this was the emergence of habitability, not merely in the sense of survivable conditions, but in the profound ability for ecosystems to take root, expand, and diversify. Tidal pools, riverbanks, and wetlands each served as crucibles for life, to experiment with new forms and strategies. Water facilitated the flourishing of evolution. There is also the intriguing matter of pH, the balance of acidity and alkalinity in Earth's waters. Early oceans were likely more acidic than they are today, owing to elevated levels of dissolved carbon dioxide. Over time, the weathering of silicate rocks aided in neutralizing this acidity, gradually shifting the oceans toward a more balanced pH, which was more conducive to life. Once again, water served as both the agent and the arena, dissolving minerals, transporting ions, and buffering changes. Then there are the salts. The reason seawater is saline is that as rainwater erodes rocks, it dissolves ions, such as sodium chloride and calcium sulfate, and carries them into the sea. Here, some are utilized by organisms while others remain dissolved, accumulating over eons. The ocean, in a sense, represents a vast repository of Earth's erosional history. However, this history is not inert. Every ion present in seawater influences its chemical properties. The salinity lowers the freezing point, the minerals affect buoyancy, and the balance of nutrients determines what can thrive. This, too, shapes life. As life evolved, it adapted not to generic water, but to the specific composition of Earth's oceans, their temperature, salinity, and mineral content. In a very real sense, life on Earth is not merely water-based, it is Earth-water-based, and the chain reaction persists. Water forms clouds, clouds scatter sunlight, scattered light cools the surface, rain falls, rivers flow, sediments bury carbon, subduction returns water and carbon to the mantle, and volcanism releases them anew. This continuous cycle, a partnership between water and rock, water and air, water and life, defines our planet. It is not a simple linear sequence, but a spiral, a self-sustaining dance driven by the rhythm of water. Having explored the ways in which water initiated tectonics, sculpted the crust, and fueled the initial stirrings of life, it is time to examine how it integrated into the deeper choreography of the planet, not as a background element, but as the principal tempo of Earth's rhythms. One of the most significant impacts of water was on temperature, influencing not only the immediate climate of early Earth, but also the vast cycles of geological time. Water, by its very nature, resists change. It warms slowly, cools slowly, and transports heat across great distances. This thermal inertia became one of Earth's most valuable assets. Let us take a moment to envision the early planet once more. Volcanoes erupted and spewed forth along newly formed ridges. The sun was younger and fainter, emitting only about 70% of its current brightness. With reduced solar output, Earth should have been frozen from its inception, a veritable snowball. Yet, it was not. Evidence from ancient zircon crystals and isotopic studies indicates that liquid water existed at least 4.3 billion years ago. This paradox, a faint young sun coupled with warm early oceans, perplexed scientists for decades, giving rise to what is known as the faint young sun paradox. Once again, water lies at the heart of the solution. Carbon dioxide, methane, and other greenhouse gases, likely released from the mantle through outgassing, formed a dense, heat-trapping atmosphere. Water vapor, itself a potent greenhouse gas, amplified this warming effect. The result was a planet that remained sufficiently warm for its oceans to stay liquid, even under a dim sun. However, this delicate balance was precarious. An excess of greenhouse gases would have tipped Earth toward a Venus-like inferno, while too little would have resulted in a complete freeze-over, similar to Mars. The crucial difference was that water did not merely participate in climate regulation, it actively managed it. Here's how. When Earth became too warm, the chemical weathering of silicate rocks accelerated. This process extracts carbon dioxide from the atmosphere, locking it into carbonate minerals. While slow, it proved remarkably effective over geological timescales. Conversely, when Earth cooled, weathering diminished, carbon dioxide levels gradually increased through volcanic outgassing, and temperatures subsequently rose. This prolonged feedback loop, mediated almost entirely by water and rock, functioned as a planetary thermostat, maintaining the planet within the Goldilocks zone, not too hot, not too cold, for billions of years. Occasionally, however, this balance was disrupted. There were periods in Earth's history when water, rather than maintaining equilibrium, tipped the planet into a state of chaos. One such instance involved the snowball Earth events, profound global freezes that occurred approximately 700 million years ago. During these periods, glaciers may have extended as far as the equator, and oceans became entirely ice-covered, transforming the planet into a gleaming white marble that reflected sunlight back into space, intensifying the chill. The precise triggers for these freezes are still a subject of debate. One theory posits that the clustering of continents near the equator led to increased weathering, causing a too rapid drawdown of carbon dioxide. With reduced greenhouse gases, the planet cooled, ice expanded, and once it reached the tropics, the albedo effect took hold, with white ice reflecting more sunlight, creating a self-reinforcing cycle of freezing. However, this is where water's duality becomes evident. As volcanic activity continued beneath the ice, carbon dioxide levels gradually increased. With no open oceans to absorb it, carbon dioxide accumulated in the atmosphere, eventually triggering a greenhouse rebound. When the ice finally melted, it did so catastrophically, resulting in massive floods, runaway warming, renewed weathering, a subsequent drop in carbon dioxide, and a return to balance. These dramatic shifts were not disruptions to Earth's narrative. They were integral to its rhythm, representing extreme movements in a symphony conducted by water. Each instance of Earth freezing or overheating necessitated adaptation by its life forms. Some perished, while others diversified, and in the aftermath, evolution surged. Following Snowball Earth came the Ediacaran period, a curious and fertile era during which multicellular life blossomed in novel ways. Some scientists suggest that the trauma of global freezing followed by rapid thawing may have propelled evolutionary progress, opening up new ecological niches. This pattern of catastrophe, followed by creativity, is deeply embedded in the fossil record, with water consistently present as the medium. Consider mass extinctions. The Permian-Triassic extinction event, the most severe in Earth's history, eradicated over 90% of marine species. It is believed to have been triggered by massive volcanic eruptions in Siberia, which released greenhouse gases into the atmosphere and caused ocean acidification. Water, once again, was both the victim and the vector, absorbing carbon dioxide, warming, and losing oxygen. Life suffocated within its own element. However, in the aftermath, ecosystems recovered, new species emerged, coral reefs re-established themselves, and life continued to find new forms within the ancient waters. Even on a daily basis, water shapes biology. Circadian rhythms in plants and animals follow cycles of evaporation and moisture. Migration routes often trace the paths of rivers. Reproduction, hibernation, and feeding patterns are all attuned to the rhythms of water. The hydrosphere not only supports life, but actively guides it. Now, we must zoom out one level further to grasp a more significant truth. Water did not merely transform Earth, it differentiated Earth. Because of water, Earth became the sole planet in the solar system with visible tectonic plates, a carbon cycle, long-lived volcanism, and life. This was not solely due to the presence of water, but because of its persistence, its deep and slow cycling, its role in carving the world, and its to moderate its internal fire. Other planets experienced water briefly. Mars possessed rivers, lakes, and perhaps even seas. Venus may have once had oceans, but only Earth managed to retain its water, buffer it, bury it, and breathe it. This is why, when searching for extraterrestrial life on exoplanets orbiting distant stars, the first indicator we seek is water. It is not a guarantee, but a suggestion, because water is not a luxury, it is a lens. It reveals which planets might be habitable, which ones can balance chaos with stability, and which ones might harbor their own cycles of chemistry and change. In this manner, Earth's oceans are more than a mere feature. They are a fingerprint, a symbol of profound stability amidst cosmic upheaval, a testament that even in the cold and darkness, a world can retain warmth and perpetuate it. And so, the chain reaction continues. Water falls, rises, cycles, carves valleys, powers storms, carrying whispers of ancient stars. It began with impacts and cosmic dust, leading to rivers and rain, and it still flows. To truly comprehend the planet's profound relationship with water, the intricate interplay of cosmic collisions, chemical reactions, and deep planetary processes, we must broaden our perspective. venturing far beyond Earth itself, even beyond our solar system. While our oceans feel intimately connected to us, almost personal, their genesis is rooted in the vast antiquity of the cosmos, stretching back through celestial bodies, past stars, and into the frigid, dark nebulae from which all known matter, including ourselves, coalesced. Let us begin with a simple yet astonishing fact. The water you consume today predates our sun. This is not a poetic notion, but a demonstrable truth of chemistry. The hydrogen within water, that exceedingly light and buoyant element, was forged in the initial moments following the Big Bang. During the universe's brief, incandescent infancy, as the first protons cooled sufficiently to allow atomic nuclei to form, hydrogen emerged. Some of this primordial hydrogen became the fuel for stars, while under specific conditions it bonded with oxygen to create water. The most ancient water ever detected, found within distant interstellar clouds, is over 12 billion years old. These nebulae drift silently and serenely through galaxies. Some portions condense to form stars, while others collapse into planetary systems. Encased within these nebulae are grains of ice. Water molecules, captured by dust particles, have journeyed through the vacuum of space for countless eons. When our solar system was in its nascent stages, with the sun still forming from a collapsing nebula, some of these icy particles were present. They were not born within our solar system, they were inherited. They survived not as pools of liquid or even solid ice, but as frost clinging to microscopic dust motes. These dust motes were eventually drawn into the solar disk, the flat, rotating plane of matter from which planets developed. In the cooler peripheries of this disk, far from the nascent sun, water ice was abundant. Closer to the sun, the conditions were too scorching for ice to persist. Only rock and metal could endure. However, gravity and turbulent currents disregard such neat demarcations. Matter migrates, and distant regions can deliver material inwards. This radial mixing of hot and cold, dry and wet environments likely facilitated Earth's acquisition of water-bearing rocks. Some scientific estimations suggest that as much as 50% of Earth's water predates the solar system itself. This implies that the molecules hydrating your morning beverage were created not on Earth, nor even in its vicinity, but in the dark expanse between the stars. This provides a much broader context. Water did not spontaneously appear with Earth's formation. It was already present, awaiting its destined place. Yet, Earth is not the sole celestial body touched by water's influence. As previously noted, Mars once harbored lakes and rivers, evidenced by dried-up deltas, intricate channel patterns, and ancient lake beds. Rovers have unearthed clays and minerals that exclusively form in the presence of water. It is even plausible that brine-rich aquifers persist deep beneath its surface. Venus, Earth's twin in size but starkly different in disposition, may have once possessed oceans, but its close proximity to the sun proved its undoing. Its oceans evaporated, and solar ultraviolet radiation dissociated the water molecules. Hydrogen escaped into space, while oxygen either bonded with surface rocks or also dissipated. What remains is a scorching world bearing only faint traces of its once wet past. Even moons in the outer reaches of our solar system reflect Earth's watery nature. Europa, one of Jupiter's moons, is entirely encased in ice, concealing a subsurface ocean warmed by tidal forces exerted by Jupiter's immense gravity. Ganymede and Callisto might also harbor hidden oceans, as does Saturn's Enceladus, a diminutive yet brilliant moon that ejects plumes of salty water into space. Titan, another of Saturn's moons, features lakes and rivers not of water, but of methane, a chemical mimicry of Earth's hydrological cycle playing out in hydrocarbons at a frigid, minus 179 degrees Celsius. Beyond our solar system, we have identified exoplanets situated within the habitable zones of their stars. Some of these may be entirely ocean worlds, devoid of any land masses. Others could be arid, desert planets or icy spheres. The exact nature of these distant worlds remains unknown, but our search continues. For if Earth's intricate watery narrative imparts any singular lesson, it is this: water fundamentally alters everything. It is not merely a solvent, it is an environment, a sculptor, a cradle for complex chemistry, and potentially an inevitable prerequisite for life. This leads us to another profound realization. Earth's water is not only ancient, it is interconnected. The hydrogen atoms within your own body may have once orbited a comet in the Kuiper Belt, or been synthesized within a star long extinguished. The oxygen that sustains your breath might have once been part of a glacier during the last ice age, or drifted as vapor through the exhalations of primeval forests. All the water on Earth is part of a singular planetary system. It evaporates, condenses, precipitates, freezes, and flows. Crucially, it does not truly depart. Not in any significant quantity, not anymore. This means the water currently within you may have previously filled a dinosaur's footprint, sculpted a canyon during the age of Pangaea, or seeped through the roots of a plant 400 million years ago. Water bridges moments. Water connects beings. It represents a shared heritage, not only across space but across time itself. And this inheritance carries with it a remarkable pattern. Every major transition in Earth's history, from a molten inferno to a blue ocean planet, from microbial mats to lush rainforests, from extinction events to evolutionary leaps, has been accompanied, or even facilitated, by water. It acts not solely as a chemical compound, but as a potent force. It cools, it erodes, it transports, it dissolves, it buffers. It is, quite literally, the medium through which change progresses. This explains why paleoclimatologists meticulously study ice cores to decipher ancient climate records. It is why astrobiologists diligently search for water signatures on extraterrestrial worlds. It is why geologists trace ancient shorelines and riverbeds to map the slow, deliberate ballet of continental drift. Ultimately, to comprehend Earth is to follow the water. And to follow the water is to perceive not a static planet, but a vibrant, breathing entity. One whose vitality pulses not only with molten rock and tectonic plates, but also with the ebb and flow of tides, the ephemeral dance of clouds, and the persistent journey of rivers. Therefore, when we pose the question, where did Earth's water originate? We are, in essence, inquiring about something far more fundamental. We are asking how the universe learned to retain warmth, how cosmic dust transformed into flowing rivers, how inherent chaos gave rise to serene order, and most significantly, how a pale blue dot acquired the capacity to emit its gentle, liquid song into the surrounding darkness. Within the hushed confines of laboratories, upon windswept Antarctic outcrops, and among the fragments of space rocks meticulously preserved in museum archives, the collective voice of human curiosity has resonated for centuries. The question, where did Earth's water originate, may sound akin to myth-making, yet it has been approached with the rigorous discipline of chemistry, the unwavering patience of geology, and the bold reach of cosmic imagination. Let us commence with a figure whose name might not be emblazoned in popular textbooks, but is spoken with profound reverence within research communities. John Valley. In the early 2000s, Valley, a geochemist affiliated with the University of Wisconsin-Madison, undertook an examination of minute crystals known as zircons. These resilient minerals possess the remarkable ability to withstand immense heat and pressure, thereby preserving a chronicle of Earth's earliest epochs. These specific zircons, extracted from ancient rock formations in the Jack Hills region of Western Australia, were over 4.4 billion years old. Within them lay a subtle yet significant indication: isotopic signatures of oxygen that suggested interaction with liquid water. This discovery was truly astounding. These were not mere pebbles from an ocean. They were temporal vessels, demonstrating that Earth possessed a stable crust and, potentially, surface water remarkably soon after its formation, perhaps as little as 100 million years into its existence. Prior to this revelation, scientists generally presumed that the Hadean Aeon, named after the mythological underworld, was characterized by a completely molten, arid, and tumultuous state for hundreds of millions of years. However, these zircons presented a compelling counter-narrative, hinting at the presence of rain, oceans, and a comparatively tranquil environment much earlier than previously conceived. John Valley did not claim to have identified the absolute first drop of water, but his work was instrumental in shifting the understood timeline of Earth's hydration further back into a more ancient and water-rich past. Yet, the intricate puzzle was far from complete. Concurrently, researchers were engaged in the analysis of meteorites, not solely for their metallic content or impact scars, but for evidence of water. This brings us to Alexander Halliday and his team at Oxford University. Employing sophisticated isotopic analysis techniques, Halliday's group began a comparative study of the deuterium to hydrogen D/H ratios across various materials within the solar system. Their particular focus was on carbonaceous chondrites, those ancient, water-rich meteorites that seem to hold resonant clues to Earth's origins. The findings were strikingly significant. The isotopic composition of hydrogen found within these meteorites exhibited a closer correspondence to that of Earth's oceans than had ever been observed with cometary samples. This marked a quiet but profound scientific revolution. For decades, comets had been considered the preeminent candidates in theories concerning the origin of Earth's water. Envisioned as dramatic celestial visitors, crashing into a parched planet and bestowing their icy bounty. However, Halliday and his colleagues demonstrated that the underlying chemistry did not align. Comets, particularly those originating from the Oort cloud, exhibited significantly higher concentrations of deuterium. The isotopic match was demonstrably off. This indicated that Earth's water must have arrived from an alternative source, something less spectacular, more rocky, and geographically closer. This realization represented a moment of scientific humility, a salient reminder that the most dramatic explanation is not invariably the correct one. Meanwhile, within laboratories such as those directed by Lydia Hallis at the University of Glasgow, analytical tools continued to advance in precision. Hallis and her team meticulously examined olivine inclusions, fragments within volcanic rocks originating from Hawaii that represent remnants of the Earth's deep mantle brought to the surface. Within these inclusions, they discovered hydrogen possessing isotopic ratios that were not only lower than those found in Earth's oceans, but even lower than those detected in chondritic meteorites. This constituted an unexpected and pivotal clue. It raised the possibility that a portion of Earth's water, or at least its hydrogen component, might have originated not from asteroids at all, but directly from the solar nebula itself. This was a bold assertion. If proven correct, it would imply that Earth incorporated hydrogen gas directly from the disk of material encircling the young sun, embedding it within its mantle during the planet's formation. Subsequently, this incorporated hydrogen could have reacted with oxygen-bearing minerals to synthesize water. It is important to note that not all scientists universally concur with this hypothesis. The debate remains active. However, Hallis's findings have reopened a long-standing possibility that Earth's water was not exclusively delivered from external sources, but that a portion may have been retained internally from the outset. The scientific inquiry has also extended to celestial missions. Expeditions such as the European Space Agency's Rosetta mission, which conducted in-depth studies of Comet 67P/Churyumov-Gerasimenko, furnished an abundance of data concerning cometary composition. Upon analyzing the deuterium to hydrogen D/H ratio of the comet, Rosetta detected a value 3 times greater than that found on Earth. This constituted another significant blow to the prevailing theory that comets were the primary deliverers of Earth's oceans. Nevertheless, each new finding introduced further nuance. Certain comets, particularly those belonging to the Jupiter family, exhibit lower DH ratios. Some samples indeed present a closer isotopic match, but as a collective group, cometary compositions demonstrate inconsistency. This illustrates the inherent beauty of scientific investigation, particularly in the realm of planetary science. It is not a narrative of universal agreement, but rather a story of converging evidence. Dozens of research teams, employing a multitude of methodologies and examining a wide array of celestial objects, from Martian meteorites to lunar basalts, have collectively begun to construct a compelling picture. Earth's water does not originate from a single source. Instead, it is derived from multiple origins. Some water likely came from asteroids, some from the Earth's mantle, and perhaps some from interstellar ice that predated Earth's very existence. Each study contributes a vital brushstroke to this complex mosaic. Each result, even when seemingly contradicting previous findings, serves to refine our understanding of the truth. Beyond the laboratory, fieldwork continues with unyielding persistence. In Antarctica, meteorite hunters traverse the frozen plains, equipped with snowmobiles and specialized tongs, collecting space rocks that have remained undisturbed for millennia. In Japan, scientists are meticulously studying asteroid samples returned by the Hayabusa 2 mission, specifically tiny grains from Ryugu, providing the first direct specimens from a carbonaceous asteroid. Every particle discovered holds a potential clue, because when it comes to understanding Earth's water, the narrative is not solely told by its vast oceans. It is also narrated by isotopes, by minerals, and by the spectral remnants of cosmic impacts preserved within rock. Furthermore, it is told by the dedicated individuals, the geochemists, planetary scientists, and cosmochemists who devote their lives to deciphering the subtle whispers of hydrogen and oxygen. They act as translators, rendering the ancient language of atoms into human comprehension and wonder. Perhaps this is the most captivating aspect of the discovery process. Not merely the empirical findings themselves, but the intellectual journeys of the minds that unearthed them. We inhabit a world where narratives are frequently conveyed through spoken or written words. But the story of Earth's water, its pervasive presence, its remarkable persistence, and its profound transformative consequences, is inscribed in minerals, encoded in isotopes, and expressed through silent, elegant equations. This is a chronicle assembled not by poets or prophets, but by a lineage of diligent thinkers equipped with sophisticated lasers, highly sensitive mass spectrometers, and an almost sacred dedication to scientific precision. Among these dedicated individuals is Meenakshi Wadhwa, a planetary scientist whose research intricately bridges the fields of cosmic chemistry and astrobiology. Her meticulous studies of hydrogen isotopes within meteorites have significantly clarified the distribution patterns of water throughout the early solar system. Wadhwa's research has bolstered the prevailing hypothesis that water-bearing asteroids, rather than icy comets, were the more probable carriers of Earth's vast ocean volumes. In a past interview, she aptly likened her scientific endeavor to the practice of archaeology, albeit conducted on a planetary scale. She articulated that each meteorite serves as a messenger, carrying within it a narrative from a time predating Earth's very existence. This profound sentiment reverberates throughout the entire discipline, as planetary science extends beyond the mere study of rocks. It is fundamentally about understanding context, connection, and continuity. The remarkable notion that we can examine a small fragment that has journeyed from the cosmos and interpret it as if it were a chapter from an ancient tome is not the realm of fantasy. It is the tangible outcome of rigorous laboratory work. To decipher this cosmic book, scientists have developed instruments of astonishing sensitivity and precision. Consider, for instance, the secondary ion mass spectrometer, or SIMS. This instrument enables researchers to vaporize minuscule points on a sample and subsequently analyze the isotopes contained therein. These sophisticated devices can measure the deuterium to hydrogen D/H ratio within individual grains of minerals like olivine or pyroxene. They possess the capability to differentiate between water molecules that are intrinsically bound within a mineral's lattice structure and those that were introduced later through surface weathering processes. Through the application of instruments such as SIMS and more recently, atom probe tomography, scientists move beyond simply studying rocks. They engage in the direct interrogation of atoms. These atomic-level investigations have led us to the Moon. Yes, the Moon, which was long presumed to be an arid and barren celestial body. However, during the early 2000s, this long-held belief was definitively overturned. NASA's Moon Mineralogy Mapper instrument aboard India's Chandrayaan-1 mission detected spectral signatures indicative of hydroxyl, a molecular group strongly suggesting the presence of water on the lunar surface. Subsequent missions provided further confirmation. The Moon indeed possesses water, not in the form of pools or oceans, but as ice trapped within permanently shadowed craters, and as hydroxyl molecules bound within lunar minerals. An even more surprising revelation followed. Certain lunar volcanic glass beads, retrieved by Apollo astronauts, contained measurable quantities of water. These samples, isotopically analyzed in laboratories decades after their collection, formed from magma, suggesting that water existed within the Moon's interior at the very time of its formation. This discovery then prompted a profound and audacious question. If the Moon originated from Earth's own mantle following the colossal Theia impact, and if it contained water, then Earth's interior must have also possessed water. This provided a critical insight, not solely about the Moon, but about Earth's most primordial stages, a silent echo of a shared cosmic history. These types of revelations, gleaned from space missions, meteorite analysis laboratories, and highly sophisticated instrumentation, underscore the profoundly interdisciplinary nature of the quest to understand Earth's water. The endeavor involves astrophysicists who construct models of interstellar cloud collapse. It engages chemists who meticulously measure the precise vibrational frequencies of water molecules under varying pressures. It includes planetary geologists who interpret craters, sedimentary layers, and tectonic fault lines as if they were intricate hieroglyphs. It encompasses computational scientists who run complex simulations of planet formation, modeling the potential survival of volatiles like water within the intense heat of accretion. And crucially, it involves engineers, numbering in the hundreds, who design spacecraft capable of withstanding the rigors of launch, navigating vast interplanetary distances, and successfully retrieving even a sesame seed-sized dust grain that might hold the key to how Earth became hydrated. The OSIRIS-REx mission, for example, returned samples from asteroid Bennu, a carbonaceous body strongly suspected of harboring significant hydrated minerals. Launched in 2016, the spacecraft reached Bennu, mapped its surface with exceptional resolution, collected regolith, and successfully returned to Earth in 2023. This small collection of asteroid dust is presently undergoing analysis in laboratories across the globe. Preliminary findings have already indicated the presence of phyllosilicates, clay-like minerals that form exclusively in the presence of water. Once again, the cosmic trail of evidence leads back to hydration. Similarly, Japan's Hayabusa 2 mission returned samples from asteroid Ryugu in 2020. Among its discoveries were organic molecules and hydrated minerals, reinforcing a consistent pattern. Water, water, and more water. What is truly remarkable is not merely the data itself, but the sheer persistence demonstrated in its acquisition. This is not a rapid process. A single analytical procedure can consume years, and a hypothesis may await confirmation for decades. Some meteorites currently under investigation were collected as far back as the 1960s. The data they contained remained inaccessible, awaiting the development of instruments that had not yet been invented. In this scientific pursuit, the endeavor is not a sprint, but a pilgrimage. And these pilgrims, the geochemists and astronomers, the spectroscopists and modelers, are part of a continuum that extends further back than one might initially imagine. In the 18th century, the German chemist Henry Cavendish achieved a groundbreaking discovery, demonstrating that water was not a fundamental element, but rather a compound composed of hydrogen and oxygen. Over the ensuing centuries, as the periodic table evolved and atomic theory solidified, water became an invaluable lens through which to explore not only the intricacies of chemistry, but also the vastness of the cosmos. Each advancement in understanding water, its molecular structure, its diverse phase transitions, its remarkable capacity for dissolution and transport, facilitated the recognition of its telltale signatures in the natural world. Thus, when we examine Earth and inquire about the origin of its abundant water, we are simultaneously asking, how have we acquired knowledge about something so profoundly ancient? The answer, invariably, lies in human ingenuity. It resides in the field teams diligently chipping meteorites from Antarctic ice. It is present in the doctoral students meticulously running isotopic samples late into the night. It is embodied in the mission planners who chart intricate courses to distant, tumbling asteroids millions of miles away. It is found within the grant writers, the data analysts, the journal editors, and the overarching systems and frameworks that support scientific inquiry. Every incremental piece of understanding we have gained regarding Earth's water has stemmed from the dedicated effort of individuals, amplified over decades. Yet, despite this considerable effort, much remains unknown. Certain scientists continue to advocate for a nebular origin, positing that hydrogen sourced directly from the solar nebula played a more significant role in the formation of the solar system role than currently understood. Others delve into the implications of water's peculiar properties, such as its anomalous expansion upon freezing, its unusually high surface tension, and its critical role in mediating the chemistry essential for life. Some researchers pursue questions regarding water's influence on plate tectonics or investigate whether deep mantle reservoirs facilitate water cycling on billion-year timescales. This is not a concluded matter. It remains an ongoing enigma. However, it is a mystery that we are collectively unraveling, transcending borders, disciplines, and decades. Our progress is marked not by declarations, but by subtle indications: the faint clink of a sample tube, the quiet hum of a laser, the slow, unwavering patience of minds that recognize the ocean's genesis began with a simple question. Beneath the surface of every ocean wave, behind each droplet of rain, tracing a path down a window pane, and within every tear ever shed lies a molecular choreography as ancient as the stars themselves. If water serves as the storyteller of Earth's past, then its narrative is not inscribed in ink, but rather etched in isotopes, those subtle, silent signatures that reveal truths imperceptible to the naked eye. To truly perceive these whispers, science must embark on a profound journey of discovery. Let us commence with geochemistry, the discipline that, more than any other, has equipped us to perceive the world through the elemental lens. Geochemists are akin to alchemists of the tangible. They deconstruct rocks, ice, gas, and water, reducing them to precise ratios. The deuterium to hydrogen, D/H ratio, a measure of the relative abundance of deuterium compared to regular hydrogen, has already played a pivotal role in our unfolding narrative. But what renders this ratio so significant? Deuterium is an exceedingly rare isotope. For every approximately 6,000 atoms of ordinary hydrogen, there exists roughly 1 atom of deuterium. However, across different regions of the cosmos and within various types of materials, this ratio fluctuates. It functions as a chemical identifier, a temporal marker, and a crucial clue. For instance, water that formed within the interstellar medium typically exhibits a higher DH ratio due to the extreme cold temperatures prevalent in such environments. Conversely, water that originated from solar nebular gases tends to possess significantly less deuterium. Consequently, when scientists analyze the DH ratio in ocean water, meteorites, lunar glass, or cometary ice, they are effectively constructing a map, not of geographical locations, but of origins. In the laboratory, the precise measurement of this ratio demands extraordinary accuracy. This is where the mass spectrometer enters the picture, a sophisticated instrument capable of segregating atoms based on their mass and electrical charge. Some of these instruments are so exquisitely sensitive that they can detect variations in isotopic ratios down to parts per million. A minuscule drop of water, vaporized and introduced into the machine, is transformed into a continuous stream of data. Each peak on the graph represents a fragment of the narrative. Through mass spectrometry, researchers have successfully traced the isotopic journey of Earth's water across millennia, revealing a striking consistency in the ocean's DH ratio that has endured for billions of years. This steadiness implies a vast, well-circulated reservoir, sustained by the planet's hydrological cycle and potentially regulated by deep subterranean reserves. To delve beyond surface chemistry and examine planetary mechanics, we turn to geophysics. One of the most astonishing discoveries of recent decades is the presence of water within the deep mantle, not as free-flowing liquid, but as molecules intricately bound within the crystalline matrix of minerals such as wadsleyite and ringwoodite. These minerals can only form under immense pressures, hundreds of kilometers beneath the Earth's surface, yet they possess the capacity to sequester substantial quantities of water, up to 1% of their mass. When considering the sheer volume of the mantle transition zone, this translates to a potential water volume equivalent to all the surface oceans combined. Our understanding of this phenomenon stems from laboratory experiments conducted within diamond anvil cells, devices that subject minute samples to crushing forces between 2 diamonds, thereby replicating deep mantle pressures. When scientists synthesize wadsleyite or ringwoodite and introduce water, these minerals readily absorb it into their structures. A definitive real-world validation emerged in 2014, when a team spearheaded by Graham Pearson identified a microscopic ringwoodite inclusion within a diamond originating from Brazil. This inclusion contained water, not in liquid form, but chemically bound within its structure. This marked the inaugural direct evidence that the mantle transition zone is not an arid expanse. This singular inclusion was akin to discovering a solitary dewdrop in a cavern, prompting the realization that the entire space might be damp. Now, let us shift our focus upward. To comprehend the initial acquisition of water by planets, we consult astrophysics and cosmology. Within protoplanetary disks, those flattened, spiraling nebulae of cosmic dust and gas that encircle nascent stars, water exists in various states. Vapor predominates in the inner regions, while ice crystals adhere to dust grains in the outer zones. The demarcation between these realms is known as the snow line, the boundary where temperatures plummet sufficiently for water to solidify. Planetary formation is profoundly influenced by this snow line. Interior to it, terrestrial planets like Earth coalesce, forming hot, arid, and dense worlds. Beyond it, gas giants and icy celestial bodies take shape, including Jupiter, Saturn, Uranus, Neptune, and a multitude of comets and Kuiper Belt objects. However, matter does not remain static. Turbulence, orbital migration, and gravitational perturbations induce mixing. Astrophysical models now simulate the process by which icy planetesimals from beyond the snow line can be propelled inward, colliding with nascent Earth and delivering water. One influential model, termed the Grand Tack, posits that Jupiter may have migrated closer to the Sun early in the solar system's history, scattering water-rich asteroids towards Earth before migrating back outward, much like a sailboat tacking against the wind. This early celestial dance could elucidate the transport of volatiles to the inner solar system. These models are not mere speculation. They are encoded within extensive simulations executed on supercomputers, calibrated with observational data, and validated against the isotopic compositions and dynamical characteristics of the solar system. Even the composition of exoplanets, planets orbiting stars beyond our own solar system, contributes to refining these concepts. When we detect water vapor in the atmospheres of hot Jupiters or ascertain the density of super-Earths, leading us to hypothesize they might be ocean worlds, we gain insights into the prevalence or rarity of Earth's specific water story. And what of the chemistry underpinning life itself? Biochemists investigate how water's distinctive properties facilitate life's existence. Its polarity, its capacity to dissolve salts and proteins, its substantial heat capacity, and its peculiar expansion upon freezing. All these unique attributes render water not merely beneficial, but indispensable. Some researchers even propose that water's peculiarities are not coincidental, but rather essential prerequisites for life to emerge anywhere in the universe. In this perspective, the genesis of life is not solely a consequence of carbon and time, but of water's specific capabilities. They argue that no other solvent possesses quite the same equilibrium of reactivity, stability, and versatility. This brings us to the ultimate frontier of this scientific inquiry. Time. Radiometric dating. Based on the decay of isotopes, such as uranium to lead or potassium to argon, allows us to assign precise ages to geological materials, from meteorites and lunar samples to Earth's most ancient zircons. Employing these temporal markers, scientists have constructed a timeline. Earth originated approximately 4.54 billion years ago. Zircons suggest the existence of a stable crust and hydrological interaction by 4.4 billion years ago. Carbonaceous sediments appear by 3.8 billion years ago, and evidence of life emerges by at least 3.5 billion years ago. Throughout this entire epoch, water was not a late arrival, but an active participant. The deep scientific evidence unequivocally demonstrates that Earth's water was not an afterthought. It was present during accretion, it played a role in differentiation, it influenced climate, and it laid the groundwork for biology. It is not a minor detail, it is the unifying element, the narrative thread that binds the Earth together, from molten rock to towering mountains to microscopic organisms. And the more we investigate it, the more we realize it extends beyond mere origins. It encompasses what water has made possible. From the moment liquid water began to interact with the young Earth's cooling crust, it commenced its prolonged and silent work, shaping life and charting the course of change. Yet, water did not hasten this undertaking. It proceeded with deliberate patience, sculpting valleys over millennia, modulating climates across eons, and offering its embrace to the earliest, most fragile sparks of life. And when life did eventually emerge, water was not merely present, it was fundamentally essential. Within those primordial oceans, characterized by their acidity, warmth, and agitation from hydrothermal vents, chemistry truly came alive. Here, amidst the rich mineral plumes ascending from the seafloor, molecules found the requisite energy and structural scaffolding to replicate. Amino acids assembled, RNA strands formed, and simple lipid vesicles evolved into nascent cells. While the precise origin of life may remain an enduring mystery, nearly every credible hypothesis situates its genesis within or in close proximity to water. The reason? Water facilitates movement, enabling molecules to drift, collide, and interact. It dissolves essential nutrients, aids in the folding of proteins, and mediates the flow of ions. It acts as both the medium and the message. For the initial billion years, life remained microscopic, unicellular, soft-bodied, carried along by the currents. However, over time, water began to host more than mere chemical reactions. It evolved into a crucible of complexity. Photosynthetic microorganisms, such as cyanobacteria, commenced releasing oxygen. Gradually, this gas accumulated, first within the oceans and subsequently in the atmosphere. The great oxidation event was not an abrupt explosion, but a gradual yet irreversible transition. Oxygen proved toxic to many of Earth's original anaerobic inhabitants, leading to widespread extinctions across the microbial world. Nevertheless, oxygen also facilitated novel metabolic pathways, opening up new possibilities. The biosphere, previously confined to anaerobic life forms clinging to hydrothermal vents or fermenting sugars in perpetual darkness, began to expand. Oxygen permitted the development of larger cells, specifically eukaryotic cells possessing nuclei, organelles, and intricate internal structures. From these evolved forms, multicellular life would eventually arise. However, further setbacks were yet to come. The Proterozoic eon, spanning from 2.5 billion to 541 million years ago, was a protracted and peculiar period. Sometimes referred to as the boring billion, it was anything but uneventful. Life diversified subtly. Complex cells emerged, and ecosystems evolved in intricate ways. Yet, to the naked eye, little appeared to change. While beneath the surface, water continued its cycle. Continents drifted, oceans opened and closed, tectonic plates collided and separated, and sediments accumulated, bearing the chemical imprints of evolving life. Then, approximately 720 million years ago, Earth experienced a profound freezing event. Glaciations enveloped the globe, potentially reaching as far as the equator, occurring twice during the cryogenian period, transforming Earth into a veritable snowball. Oceans became sealed beneath ice, photosynthesis ceased, and most life likely retreated to geothermally heated refuges near hydrothermal vents or within subglacial meltwater pockets. This represented one of life's most formidable challenges. Paradoxically, water, while posing a threat, also served as its salvation, for liquid water persisted beneath the ice. Upon the subsequent melting of the glaciers, they released vital nutrients into the oceans, triggering massive blooms of algae and microbes. Oxygen levels surged, and life experienced a remarkable resurgence. The Cambrian explosion followed approximately 541 million years ago, a period marked by an astonishing proliferation of animal life. Trilobites, worms, early vertebrates, and the appearance of shells and skeletons characterized this era. Predation evolved, and for the first time, the fossil record opened dramatically, revealing the bizarre and beautiful ingenuity of life. This diversification unfolded within aquatic environments. Marine ecosystems became the stage for evolution's most daring experiments. Filter feeders, swimmers, burrowers, coral reefs, shoals of fish, and cephalopods with their inquisitive eyes, pulsing jellyfish carried by the currents. The land, still largely barren, awaited its turn. When life eventually transitioned ashore, initially as mosses and liverworts, followed by insects and amphibians, it carried water within every cell, in every breath. Even today, every terrestrial organism remains fundamentally aquatic. We carry the chemical composition of the ocean within our blood, our sweat, and our tears. Water was the original womb from which we never truly departed. However, Earth's history is not a linear progression. It is characterized by cycles, interruptions, and new beginnings. Mass extinction events have swept across the planet 5 times in total. The Permian extinction, occurring 252 million years ago, witnessed the disappearance of over 90% of marine species, possibly triggered by colossal volcanic eruptions in Siberia, which rendered the oceans acidic and anoxic, devoid of oxygen. Once again, water became an inhospitable environment, yet recovery ensued. Fish reappeared, coral reefs were re-established, and the seas gave rise to the ancestors of dinosaurs, birds, and mammals. Each time life was severely set back, it regenerated first within the aquatic realm. Following the Cretaceous-Paleogene extinction event 66 million years ago, when an asteroid impact concluded the reign of the dinosaurs, the oceans once more provided a sanctuary. Tiny plankton, forming the base of the marine food web, rebounded swiftly, and marine ecosystems healed. Whales and dolphins would eventually evolve, coral reefs would flourish, and eventually humans emerged, constructing vessels, charting maps, pursuing fish, and examining tide pools with inquiries predating language itself. Throughout these transformations, water persisted. It not only supported life but also adapted alongside it. The composition of seawater evolved, salinity levels fluctuated, and ocean currents shifted in concert with continental drift. Ice ages advanced and retreated, and sea levels rose and fell. Each alteration redrew coastlines, fostered new habitats, and prompted migrations. Even presently, the thermohaline circulation, the global oceanic conveyor belt, regulates Earth's climate. Warm water journeys from the equator towards the poles, cools, descends, and circulates back. This vast system distributes heat, influences precipitation patterns, and replenishes ecosystems with nutrients brought to the surface. Without it, monsoons would fail, forests would wither, fisheries would collapse, and freshwater, that precious fraction of Earth's total water, forged its own distinct legacy. Glaciers sculpted valleys and formed lakes. Rivers served as conduits for civilization, and aquifers stored rainwater for millennia. From ancient wells to contemporary desalination facilities, humanity has consistently sought, venerated, and contended for freshwater resources. We are, as Leonardo da Vinci eloquently put it, conduits for water. It flows through us. We redirect it, bottle it, waste it, implore for it, yet it continues to flow. Even now, water remains the vital thread that maintains equilibrium on Earth's surface. It stabilizes the climate, moderates temperatures, reflects sunlight from snowpack, absorbs atmospheric carbon through rainfall, and transport sediment, nutrients, and seeds. Beneath the surface, within the mantle, water continues its cycle, subducted in tectonic plates and returned through volcanic lava, thereby sustaining the deep internal balance of our planet. It is easy to overlook this fundamental truth. We often perceive oceans as eternal, rivers as a given, and rainfall as inevitable. However, every single drop possesses a history. Every molecule was forged in stellar furnaces, traversed the vastness of space, arrived either as stony fragments or as vapor, and ultimately became integrated into Earth's immense, slow respiration. And within that breath, life has thrived, faltered, and resurged, consistently accompanied, embraced, and shaped by water. Therefore, the next time you take a sip from a glass or listen to the rain drumming on your roof, remember that this is more than just liquid. It is a legacy, Earth whispering its most ancient narrative. Observe your surroundings now. The sky may be veiled in clouds or brilliant azure. The ground could be saturated, frozen, or as parched as dust. But somewhere above, below, or within, water is quietly, persistently in motion, whether as a fine mist, a gentle trickle, or a rhythmic pulse. Earth is breathing, and that breath is moist. And we, you, I, all of us, are integral to that movement. We frequently forget this, discussing water as if it were external, a mere commodity to be managed or extracted. In reality, it serves as a mirror. By studying water's odyssey, we are, in essence, examining our own. Because every droplet of water on Earth, ancient, restless, and seemingly immortal, narrates not only the story of planetary formation, but also the very essence of what it means to be alive here and now, in this fleeting moment. It is remarkable to consider how recent our comprehension of water's pivotal role truly is. Merely a few centuries ago, we regarded water as one of the classical elements, unchanging and indivisible. We were unaware of its molecular structure. We did not grasp its capacity for memory, not in a mystical sense, but in a scientific one, the kind imprinted in isotopes, sediments, glacial layers, and salt flats. Today, we map underground aquifers using satellite imagery, sample comet tails with interplanetary spacecraft, and can observe a droplet forming in extreme slow motion, witnessing the physics of surface tension unfold with captivating grace. Yet, despite our advanced tools and sophisticated models, water's implications continue to elude complete understanding. This is because the narrative of water transcends mere geological or chemical processes. It possesses a moral dimension. We inhabit an era where climate change is no longer a theoretical concept. Glaciers are melting at an alarming rate. Sea levels are steadily rising. Droughts are intensifying, and floods are becoming more severe. Rivers are running dry, leaving cities parched. Water, once our inherited birthright, is increasingly becoming our profound responsibility. The very mechanisms that rendered Earth habitable, that regulated its climate, recycled its carbon, and controlled its temperature, are now being strained by human activities. We have altered the atmospheric composition, deforested critical catchment areas, constructed dams, diverted watercourses, and depleted reservoirs. Despite this, we continue to rely on water to somehow absolve us. We anticipate the arrival of rain, the melting of snow, and the refilling of reservoirs. However, nature does not guarantee equilibrium. It actively maintains it through complex feedback loops, cyclical processes, and inherent consequences. Nevertheless, even in this challenging scenario, hope persists. Just as water originally created the conditions conducive to life, it can also foster a sense of humility. A river teaches patience, an aquifer imparts the necessity of foresight, and a glacier exemplifies endurance. And when we actively protect water, when we restore wetlands, mend watersheds, and curtail pollution, we are not merely conserving a resource. We are participating in a grand narrative that commenced long before our existence, and, if we act wisely, will continue far beyond it. This story stretches from the primal stardust to the promise of future sustainability. It connects the hydrogen within your very blood to the hydrogen found in a comet's tail. It links the oxygen you inhale to the oxygen initially released by ancient algae drifting in shallow seas. It serves as a potent reminder that we are not detached from Earth's intricate systems. Rather, we are interwoven systems within systems. Water within water, consciousness within chemistry. And if Earth's past has imparted any significant lesson, it is that resilience, while real, is not an immutable guarantee. The planet has successfully recovered from asteroid impacts, supervolcanic eruptions, and devastating mass extinctions. Life has tenaciously clawed its way back from the brink repeatedly. However, such recovery processes require immense spans of time, spanning millions of years, entire epochs. We, however, do not possess that temporal luxury. We are not the dinosaurs, caught unprepared by a cataclysmic celestial event. Instead, we are the first species to possess the capacity to comprehend the atmosphere, to meticulously track carbon dioxide levels, to measure the extent of polar ice, and to model ocean currents. We are the first to witness Earth's water systems in real time, not as a passive backdrop, but as critical indicators. And crucially, we are the first to be presented with a genuine choice: to regulate the flow of water with gentle consideration, to plant a tree, to advocate for the preservation of rivers, reefs, and rainfall. We must remember that every bottle, every flush, every pipe represents a connection to a cycle far older than human language. This is not about assigning blame, it is about gaining perspective. Water arrived on Earth through a tumultuous history of violence, collisions, impacts, and inherent chaos. It achieved a state of serenity through balance, cyclical processes, flowing motion, and evolutionary adaptation. It became imbued with sacred significance through its use, by quenching thirst, nurturing fields, and playing a central role in religious rituals. And now it awaits, not our adoration, but our active partnership. For we are not separate from the oceans, we are intrinsically composed of them, not metaphorically, but literally. Your tears, your sweat, your blood, your entire being echoes the same primordial molecule that descended from space, steamed forth from magma, cooled to form terrain, gathered in ponds, and ultimately gave birth to your ancestors. Therefore, let us honor this profound narrative, not with imposing monuments or elaborate myths, but with diligent care, with enlightened policies, with equitable distribution, with cleaner industrial practices, and with compassionate choices. Let us do so with the understanding that when we safeguard water, we are simultaneously preserving the memory of distant starlight and ensuring the potential for future dawns. And so, we arrive at the threshold of a story that predates mountains and possesses a depth exceeding time itself. We have traced water's journey from the frigid extremities of space to the Earth's fiery core. We have observed its descent, ascent, transformative power, and cyclical return. We have witnessed its role in nurturing life, presenting challenges, and carrying it through fiery cataclysms and glacial ages. And we have gained a glimpse into how it continues its silent, vital work, holding together the disparate elements of this fragile yet magnificent planet. Perhaps now we can reframe our inquiry slightly. Instead of merely asking where water originated, let us ponder what it truly signifies to belong to a world fundamentally composed of water. To recognize that your heartbeat, your very breath, your thoughts, are all subtly stirred and sustained by the same ancient current that eroded continents and elevated whales. To appreciate that the vessel in your hand holds echoes of comets, of clouds, of crocodiles, and of poets. To understand that nothing you interact with, no fruit, no book, no bird, exists independently of water's quiet, essential signature. And in turn, to realize that you are an integral part of that grand cycle, not a passive observer, but an active participant. Therefore, treat the rain with respect. Walk with gentle steps beside the stream. Let your awe manifest as action. For wonder is not merely an emotion. It is a conscious choice, a perpetual act of rediscovering the miraculous within the ordinary. Thank you for accompanying me on this exploration of Earth's most enduring element. If this narrative has resonated with you, sparking a question, evoking a memory, or igniting a ripple of wonder, please feel free to share your thoughts in the comments below. I would be delighted to learn what water signifies to you. And if you wish to engage with more narratives of this nature, slow-paced, in-depth, and rich with quiet scientific insight, please consider liking, subscribing, and joining us again. We have only just begun to unravel the intricate threads of Earth's ancient saga. Until then, remain curious, remain kind, and remain fluid. This has been Secrets of History at Night, and I look forward to seeing you downstream.